Today we are going to be more formal to introduce logic. Okay, and logic actually, for the time being, is the most important part for computer science. Because so far all the computer we have are binary. Well, but in the future we may have quantum computer. In quantum computer, it's not binary. It will no longer be binary. It may have different number system they can mount. Okay, but so far on our computer we are on binary. So binary basic 0 and 1, and our Boolean variable, so-called we call Boolean. The Boolean variable will be true and false. Are you okay with this?
Yeah.
So
Yeah.
Okay. Then why is called Boolean variable? Why is called Boolean or Boolean logic or something?
Because it's true. I don't know.
Well, there is a guy called Boolean.
Oh.
Okay, there is a person called Boolean. Okay, so that's why we have to look at it's a Boolean data type, Boolean person. There's a guy called George Boole. Okay, so this guy George Boole, 15, England. Okay, this guy is born in England. So his lifetime is somewhere like he stayed like 1864. So what time span he actually lived on? You know, this guy probably is at the same period of time as President Lincoln, right? Because the President Lincoln about assassinated around the similar age. Okay, so it's the early first half of the 19th century. Okay, this is the guy, and he actually his main work is on Boolean logic and Boolean logic and Boolean algebra. So here is some analysis he said, and he worked on the symbolic logic. Okay, this is called symbolic logic. Symbolic logic. There's another word called formal logic. And what else? There's another kind of predicate logic. What is predicate logic?
I don't know.
If it rains, right? Then what? The ground is wet. Okay. Some basic logic is like if it is rain, then the ground is wet. So if this is true, if this is valid a valid logic statement, if that is a correct logic statement, then if the ground is wet, that it actually rained?
Yeah.
No.
Oh.
The ground is wet. Maybe a guy who actually spilled some water on the field. On the ground. Okay. So if it rains, it is one cause like to make the ground wet. But the ground is wet, you cannot conclude that, but it is the only reason is because it rains. So it doesn't go the opposite way. It doesn't go the opposite way. Okay?
Okay.
It doesn't go that way. But if it doesn't rain, then if it doesn't rain, the ground is wet or not wet?
If it doesn't rain?
Yeah, if it doesn't rain.
The ground is not wet.
No, the ground we don't know.
Oh.
Okay. So these are so-called predicate logic. So in your real life, like philosophical problem, actually will deal with that, but it's actually more it's more verbal. Okay. Now, what is formal logic? Formal logic doesn't work like that way. Okay. formal logic doesn't work like in that way. Formal logic is different. We need to be able to formulate it. And so we would say, if we have a P means it rains. Then we have a symbol called this, and then we will say Q. Q is the result. Say it actually the ground, the fact that ground is wet. Okay. So with this thing, we can talk about for P to become Q, to infer Q, we have P and Q, and we have 4 conditions. We have this one 0, 0, 0, 1, 1, 0, 1, 1. Okay, so here we have let's look at not P or Q. Not P or Q, not P or Q. So here is 1, 1. Or Q, Q is 1 over here and 0. Okay. The logic on the left-hand side, if it rains, the ground will be wet. Actually means the same thing as not P or Q. Why? Because if it rains, then the ground will be wet, right? So this is true. But it doesn't rain, whether it's the ground is true, ground is wet or not wet, it still be true, right? Because it doesn't matter, we don't care, right? But there is only case that will be false. That is, you actually rain, but the ground is not wet. Then that doesn't follow this logic. Is that okay? So this we call it formal logic. Formal. Formal means that we try to formulate it, or in some kind of some way to represent it. Is that okay?
Yeah.
Okay, so for this formal logic, you just remember this case. It rains, but the ground is not wet. Then it doesn't follow our logic. In this logic, we say if it rains, the ground will be wet. Okay, so for example, I make a statement that if you run 2 miles a day and then 10 days after, you will lose 10 pounds. Okay, and if you do like 2 miles a day and then 10 days after, you just lose, you don't lose 10 pounds, you lose 1 pound. Okay, then my statement of I make a statement like if you run 2 days, 2 miles a day for 10 days, and then you will lose 10 pounds. The statement would be false, right? It's not valid actually. Is that okay? So that's the only case that you make. But if you didn't run for 2 miles for 10 days, then whether you are down by 10 pounds, 20 pounds, 1 pound, it doesn't matter, because the predicate on the left-hand side, the condition doesn't happen, right? It doesn't happen. So whether it actually happened, you lose 10 pounds or not losing 10 pounds, it is actually the logic cannot be valid. Cannot be. You cannot prove that your precondition is true or not true. So in both of these cases, we don't care. So we both write down as true. Okay. And if you actually work on around 2 miles a day and then 10 days, and actually you drop 10 pounds like 10 days after, then this statement is true. So there are 3 true cases and 1 false, and this is called formal logic. Okay. So here is formal logic. So right here I use 2 representation. One is 1 predicate and 1 logic condition, like this. The other one is P bar, that means not P. Not P. And this one means or, this one means and. okay, and then Q. So it's not P or Q. Not P means like whether if you actually there's no rain, and then or this one is actually the ground is wet. Okay, this is the logic. Okay, so here I talk about this so-called formal logic, but there are several ways to represent logic. Okay, in Java's way, we have say Boolean variable a equal true, b equal false, right? And then we have a not a, and then we have a and b, and we have a or. Okay, that's Java. Second way, we can represent it as Boolean. We can represent it as a Boolean logic. So we will write here, we'll write A. This one we will write B. This one we will write A bar. Okay. This one we will write A or A and the B, and this one cap. And this one we will write A or B. That this representation is called Boolean logic. And third way to represent it, we call it Boolean algebra. I'm sorry, algebra. Okay, and here we write A, here we write B, here we write not A, here we write A times B. This one we write A plus B. Okay, any one of these actually are equivalent. So can you write down this table?
Yeah.
Can you just write down this table? These three are the same. Okay, so this here says say the same thing. Here say the same thing. Okay. I didn't write the line for the rest of it, but try to write this down. So Java expression, Boolean. Okay, I missed something here. Let me write that. Boolean logic here, we write if it is true, a equals 1, this one equals 0. Same thing here for the logic. Here equals 1, here equals 0. So 1 is representing true, 0 representing false, and then time you have a multiply symbol represent and, plus sign represent or. Okay, and the cap sign or V sign actually used for Boolean logic. So if you see something like red one or blue one, it is fine, but they are not actually representation for Java. Just write this down, and I'm going something teaching you something else.
Okay, then.
Okay, then I'll clear this. Okay, the next thing I'll cover is, since we had this, so now let's look at this logic. We have 0, 0, 0, 1, 1, 0, 1, 1. Right? We have A, B. What's this? A times B means what?
A times B is A and B.
A and B. So this one's 1. The rest of them are false. Okay. Then A plus B is what?
A or B.
A or B. So actually, it's any one of these, right? If there's A or B happen, right? It'll be like this. The third symbol is called like this. This guy called inclusive OR. Inclusive OR means 0, 1, 1, 0. That actually can only allow one of them to happen. we write down, sometimes we write down the XOR. It's called inclusive OR. Is that okay? It's called inclusive OR. That means if only one of them can happen. So inclusive OR happen will apply to where?
If you win or lose something.
Yeah. There's only one winner. There won't be, or someone be the chairman of the committee or something. It won't happen like Nancy is the chairman and the boss. Nancy is the chairman and then Carol is also a chairman. That won't happen. That actually is inclusive OR. Is that okay?
Yes.
And A is rich and the B is rich. That's possible, right? A is rich or B is rich is possible, right?
Yeah.
But A is number one and B or inclusive or B is number one. It can happen that both of them, unless that you allow tie. But if the tie is not allowed, it won't happen. Okay. So this is called Boolean. This is called truth table. This one we go here. It is called truth table. This kind of listing 01, we call it truth table. Can you copy this truth table down as well?
Okay.
There is a website called electrical for you website, okay, and they have a whole Boolean algebra, truth table, binary, arithmetic, polynomial math, or something. Many different topics you can look at it. Okay, so this one I just passed to your not here. Pass to your Facebook. Okay, I pass to your Facebook. So today I don't want to spend too much time on this because that would dig deeper. But here it has the De Morgan rule that we are going to talk about later. It all has this different mass or something over there, right? Okay, that's a De Morgan rule, and in the AP isn't it needed, but right now I'm not going to cover it. And then there's a binary addition, binary arithmetic, binary subtraction. All of these are binary, okay? And then there's this one Boolean algebra. Okay, so you talk about and or not, right? Let's look at here, okay? Let's look at here. These we will cover, but the rest of them, today we only cover this one Boolean algebra and the De Morgan rule. Okay. First, and 0 and the 0 is 0, 0 and the 1 is 0, 1 and the 0 is 0. So and will both happen, it will happen, okay?
Alright.
Or it's like if one of them not happen, it will happen. So this is plus sign. So if you look at the mass, if you have a 0 times 1, it also equals 0. Something like that. But except the only exception that is different from normal mass is this one is actually back to 1. Okay, it doesn't give you 2, 1, 0. Okay, in Boolean operation, is that okay?
Yeah.
And if you see a symbol like bar on top of it, it means like negation. So basically this one, if sometimes you write like this, or sometimes you write like this, and -1 actually equals 0 in Boolean. Okay, that's called NOT operation. So in Java, we actually have, let's say we have a variable, Boolean variable A, and then we will write down exclamation mark A. That this one is the negation of A. So, for example, we started from a variable that's 1, right, or 2, right, and then we say not A. So if there is statement so called A equals not A, right, and initially my and my A is true. Right? This is the in Java notation. Okay. So initially I'm on 1, but I actually run this once, then I'll become 0. And then I run the second time, the same thing I run again, I go back to 1. And then I write the same one more time, I'll go back to 0. One more time, I'll go back to 1. Okay, this is called toggler. Toggler. Okay. Now let me show you how toggler is useful. Okay. Let me write a Java program to show you how toggler is useful. So here I write a program called toggler. Okay, toggler means changing. Okay. So I have a program called toggler. Are you able to see my code, or do I need to zoom in or no?
I can see.
Okay. Let me change the larger font. Okay. So okay, right here, okay, stable, so right here I have a program, and I say boolean. Let me say a equals 2, right? And while, okay, and here I say int. Let me see, intr. Let me convert this. I will say for int I equals 0, I less than 10. I totally run 10 times. I increased. Okay, I run 10 times, and each time I would say, at the end of it, I would say a equals not a. And before that, I would say if a system.out I am happy. Okay. Else system.out print I am not happy. Okay. So here initially I set my a to be true. I come in here, I equals 0, I come in here. And then I would print, oh, okay, a is true, so I'm happy. And then here I reset my a to become not a. So a is true, not a is false. So my a becomes false. I go back to here, I become 1 because it increase over here. So it become 1, so I'm not, now a is false. A is false, so this is not true. So I come to here saying I'm not happy. And I'm not happy, so I print I'm happy, and then I print I'm not happy. And then come here, my a is false, not a is true. So then my new a becomes true. I'll go back to here, I equals 2. So in I equals 2, a is true, then I will print happy. So I will be changing happy, not happy, happy, not happy, happy, not happy, happy, not happy. For how many times? Totally 10 times. 10. Okay? So compile, and then I'll run. Right? So I get a result of happy, not happy, happy, not happy, happy, not happy. This is called toggler. So toggler statement is very simple. At any time you want to change, I just write something different. Is that okay?
Yeah.
So here actually I can also write. Actually, I can also write here. I can change this statement like this. Okay, I just will use that I'm happy or not happy as an example, but this one, actually, I can change it to this. It will still work, okay? Right? So if you 0 is even, 1 is odd. Is that okay?
Yeah.
This I call it toggler. So that is one use of the logic. So basically, we actually have something we want to achieve, right? So we have something we want to achieve, and then we actually, let me clean this one. We have something in our mind that we want to achieve. Say we want to change it between, we want to change it between, right here we have something we want to achieve. We want to change it between 1 or 0. We want to change it between true or false. We want to change it between even, odd. Right? All these can be achieved by toggling, right? And then we go into the logic design. The logic design is pretty simple. Initially, we have this, and then every time we want to change, we execute this. So this part is called logic design. How can I design my logic to make my sort, my computing sort happen? Right? I want to achieve something like this, but I need to have my program that work for me, like changing just exactly the way I want it. So this part is called logic design. So we design program, logic design is a large part of it. Many times we are actually dealing with logic design. Okay, so this one is an example of two-way toggler. But can we do something as a three-way toggler?
Yes.
How
no.
can you?
No.
Can you do it? Show it for me.
I don't think you can do it.
We actually can.
Oh.
We actually can. Yes. We actually can. But you can use logic to do it, or we can actually use different things like to do it. So let's assume that we want to do 0, 1, 2, three-way toggler, right? So
Yeah.
initially I set my a equals 0, but this time I need to use the integer, right? And then a equals a plus 1 take modular by 3. This one will do three-way toggler for me. Okay, so the first time I have a equals 0, right? Then the second, when I want to change it, say let's assume this is a change statement. I do the first time change statement here. A0 plus 1 equals 1, take modular by 3, I end up with 1. So I'm here. Second time, I read this again. I'm 1 this time. I plus 1, I become 2, take modular by 3. As a remainder, I get 2. Right? And then the next time I come here again. Let's use this purple. This time I'm 2, I plus 1, and become 3. Take modular, it becomes 0. And then it repeats. So this is a three-way toggler, but I use integer to achieve three-way toggler. Can you draw down this and the two-way toggler by yourself? Is that okay? Draw down in your notebook. Okay. These are very important, okay? I'm trying to teach you how to do three-way. So there's one way to, there's a two-way toggler, three-way toggler, four-way toggler. continue on. You can do whatever way you want to do. So here, today I teach you more about logic. Actually, I'm not teaching you something like a program, Java, right? Today I'm actually not teaching you any Java or something. But I'm teaching you some logic, basic logic, how you think about something. And that is very important part when you do programming. Now, let me actually ask you. Here I have a month, right? January something to December. This one's 1, this one's 12. How can I do my target as a month? Go back and repeat.
You do like the three-way toggler?
You need to have 12-way toggle, right?
Yeah, so you do like,
But 12-way toggle will give you 0 to 11.
Oh.
Right? So
Yeah.
what should you do? So you should have a 12-way toggle plus 1.
Yeah.
Right? Okay.
Yeah.
Based on this, initially I set my a equals 1. Right? I use integer. Then my a plus 1 10 modular by 12. This part give you 0 to 11, right? Plus 1.
So it goes from 1 to 12.
Yeah.
Okay.
Let me erase this. This is not pretty. Okay, let me rewrite it. Okay. So this one will give you the 12-way toggler, but coming from 1 to 12. Because this part right here, the first time I'm 1, right? And then the second time when I come to here, it's 1 plus 1 modular by 12 is 2. Okay, then I continue to do this whatever. The first time is actually 1. Okay, sorry. So here I initially should set to 0. Okay, because I have a plus 1 there. So first time I have a 0. So then I actually set this for the first time. Okay, initial condition I need to run this once. So then I have my 0 plus 1, I become 1. Wait, let me see. Actually, initially I have 0. Let me see. Probably initially I need to set to minus 1. Okay, let me set it to minus 1. I'm sorry. Initially I set to minus 1, right? So actually let's do this. Initially I set to minus 1, and then I run this once. So after the first run, actually I have, okay, I have minus 1 plus 1 10 modular by 12, that's 0, plus 1, that's actually 1, right? And then I keep doing this, actually it will be circulating at 1 to 12. Is that okay?
Yeah.
So basically, first time I need to actually do this and also run the delta function once. Okay, then I'll get initial condition to be 1. After that, each time I run a delta. Is that okay?
Yeah.
Then I'll be able to finish this 1 to 12 changing.
Okay.
That's called tabular. Is that okay?
Yeah.
So this is called tabular. I'm trying to teach you the logic. Okay. Now let's go back to our here. Okay, we have that not a, and then if some logic and 0, that actually should be 0. Okay. I have money and 1 equals 0. Whether you have money or not, it doesn't matter. 1 doesn't equal 0. So I have money and 1 equals 0 actually is 0. It will never happen. And I have money and 1 equals 1. Then actually it always be, I have the logic value always be equal to I have money. either or you have money or not having money, but you actually end up with this. Is that okay? And then this one, A and the A actually equals A, no change. A and the not A equals 0. Why? I'm rich and I'm not rich. Actually, it won't happen at the same time. So this one is 0. Is that okay?
Yeah.
Okay. And then this I'm rich, or I'm rich, or 1 equals 0. Then 1 equals 0 is false, but it doesn't matter because it's or. So if I happen, it doesn't care. I don't care about it. It's actually give you A. And I'm rich, or 1 equals 1. 1 equals 1 always should be true. So or it always I'm rich. It doesn't matter whether I'm rich or not. 1 equals 1 always happens. Okay. And the one I'm rich or I'm not rich, either way have to be any one of it. So that's true. Is that okay? I'm rich or I'm rich. It's the same as I'm rich. Okay, so that's the dual. The next one is called cumulative law for Boolean algebra. So A plus B plus C equals A plus C plus B. So you actually can change order any order. And then times the same thing. It's like math, so nothing to worry about. And then distributed law. Associative law, I'm sorry. Associative law. It doesn't matter which one operate first, so it doesn't matter. And this one is distributed law. A times B plus C equals A times B plus A times C. Similar, this one is also true, but in math, this is not true. Okay. In math, this is not true, but in Boolean algebra, it's true. Okay, so you remember to come to this website to study. I don't want you to write it. It's too much, okay? But A and the B or C is equal A and the C, B or A and the C, okay? So this is a different parameter. I'm rich, or this B is I'm tall, or I'm educated, okay? So I'm rich and I'm tall, or I'm rich and I'm educated. This actually can be distributed because the logic has no connection at all. Rich, tall, and educated, 3 factors actually doesn't matter. So you actually can distribute it. Is that okay?
Yeah.
So the next one, you have this. And then there's a redundancy law. Redundancy law like this one, A and this one actually, that I can simplify. Say this one, I have this A and A plus A bar and A. So this one equals what? This one equals A plus A bar equals A, because this one is 1. So A times 1 equals A. So the whole thing is A over here. This part, A or AB, A or AB, A or A and the B is what? I'm rich, or I'm rich and I'm tall. So I'm rich and tall doesn't matter because I'm rich. The next one, I'm rich and tall. If it doesn't happen, I'm rich is true already. So this one actually is taken away as well. So it becomes A and not A and B. Is that okay? A or not A and B. So to prove it, okay. To prove it, this is to prove it, we just do this truth table. So the whole thing right here is equivalent to this. So it becomes something like this. And this one, if you further look at it, this one actually equivalent to A or B. So the whole thing after this operation, it becomes A or B. Because it's the same with A or B, right? Either one of it is 1 is 1. So here, eventually, if you look at here, it's actually equivalent to A or B. So you can use truth table to prove it. That the whole thing right here eventually is the same as A or B. So how to prove it? The first part, we actually end up with, we actually simplified it, so eventually we become something like this, right? So then I want to prove this equals this. I use truth table. Is that okay? So at that stage, I want to prove that the two are equivalent. I use truth table. So when I use truth table, I put down my A and B, and then I put down my not A and the B, right? Because I know my A and B, so I can actually write this. Besides A, I can write the A bar, it will be 1, 1, 0, 0. So here, I can calculate 1 and the 0, that's 0. 1 and 1 is 1. And then 0 and 0, that's 0. 0 and 1, that's 0. So I get this one. And then this one, or with this one, I get this one. Right? And then I also use the A and B. For 2 or together, I get this one. And then I compare this and this, 2 are the same. So actually, A plus B equals A plus A bar and B. So 2 are equivalent.
Okay. Oh, yeah.
By what? By truth table proven. Okay? Is this okay or too tough? Somewhat not very straightforward, right?
Yeah.
So basically, you actually can simplify like this. You A or A. Okay, let's prove this one. Let's prove the second one here. Okay, let's do this. Because the previous one we proved it already. Let's prove this one. So this one, I have my A, B right here. Right? 0, 0, 0, 1, 1, 0, 1, 1. So now I want to prove this. First, I calculate my A and B. My A and B is 0, 0, 1, 0, 1, right? Now I need what? I need my A bar. So I put my A bar on this side. I have 1, 1, 0, 0. Now I need A bar OB. So A bar OB. My B is over here. My A bar is over here. Any one of it will be true. So here is 1, 1, 0, 1. Right?
Yeah.
And A bar OB need to be ended with A. So here, no is 0. No is 0. No, this is 0. Yes, this one's 1, 1. So this one is what? This one give you this and this one. So this one is A and A bar OB. You end up with this one. You end up with this logic. So this logic is the same as this one. Two are the same. These two are the same. These two columns are the same. So we actually by this we prove this.
Okay.
You want to copy it down or no?
Okay.
If you copy it down, you can actually. So you write this equation first. A and the not A plus B parentheses equals AB. Put something on top, and then you copy the proof under it. Okay. The actual proof is not that important. The process of using the truth table is what you need to learn. Is that okay? How you build out the truth table step by step to prove it. That's what we want to teach you right now. The theorem itself is not that important actually. And something like this, where you will have to use it very often in AP exam. But right now I teach you something, but I don't actually ask you to do homework. But when in September or sometime like that, we will actually ask you to do some homework. Okay.
Okay.
Right now I don't ask you to do some homework that is in written format. No.
Okay.
I will just pick some problem from this Sync Java to as a homework, not from here. But when you are in AP level, I'll ask you to do some homework for this.
Okay, I finished copying it down.
Okay. Okay, this is called proven of equation. Okay, and you can simplify things as well. And this one, A or AB, this actually equals A because you can actually check it. Okay, and then here, fine. I don't want to go into those details for these different proving. The next thing I would like to prove is De Morgan rule. Okay, and De Morgan rule actually is taught in a class over here called De Morgan rule. Okay, so now I talk about so many things, just want to prove whatever it is over here in the De Morgan rule. But before, if we don't talk about it, you actually don't know what it is. Okay. So here, let's talk about De Morgan rule. De Morgan rule actually is not too difficult. This one equals this times this time V. So here is plus, and there's a bar. So not A or B becomes not A and not B. Okay. I'm rich or I'm tall. So I'm not rich or I'm not tall, right? I'm not. So actually it means I'm not rich and I'm not tall. This here is like I'm either rich or tall, but I'm not either rich or tall. Means I'm not rich and I'm not tall. Is that okay?
Yeah.
This is called De Morgan rule. The other one is, so eventually you need to just remember this, okay? Just remember it. And then this one, I'm rich and I'm educated. The bar, okay? I'm not rich and educated at the same time. That means either I'm not rich or I'm not educated. Is that okay?
Yeah.
So basically you have like A plus C, and then you become A bar and change these to the other. Okay? So you plus sign become my time to get out of the bar. Is that okay?
Yeah.
You actually like this one. This one you have A plus B bar equals A bar and the B bar. This changes sign when you get out of it. Okay? Okay, let me actually clean this. This is not too hard, right, so far, okay? So right here, that's exercise. A, B, and C bar. So I'm rich and I'm either tall or educated, right? I'm rich and these two have to happen at the same time. I'm either tall or educated. And then this since bar is equivalent to this one times this one bar and equals this one times this one. So what? I'm sorry, this one's or. Here is time, so here you change it to here. Okay, the first one I get out of this bar. Okay, second one actually, so here is a plus sign. Okay, so let's read it. Okay, let's read it by logic. Don't actually calculate it. Here, I am rich and I'm either tall or educated. Okay, and I'm not like this. So here I put a bar. So I'm not rich, or I'm not tall or educated. And I'm not tall or educated means that I'm not tall and I'm not educated, right? Because if you have the tall or educated, one of it, the second part will be true. But the second part, tall or educated, will have bar. That means like you are not tall and you are not educated, right? The second part will be true only when that happens, right? So the first part is like I'm rich and I'm not either tall or educated. That means like I'm not rich or I'm not tall and I'm not educated. So that actually De Morgan rule used to operate this. But the idea is like just like you take care of one label at a time. But when you get out of the label, it actually will change the end to or to end. Is that okay?
Yeah.
That's called De Morgan rule. You just need to know about how to operate it, and you have to trust your De Morgan rule. That's what it is over here. So let's read the statement here. De Morgan law. Sometimes you need to negate the expression containing mixed rational and logic operator. So here, here you have A is false or B equals false. That actually is, if we interpret this logic, it actually is A bar or B bar, and then this outside is a negation, so this bar, so it actually is A bar plus B bar equals A bar and the B bar equals A and the B. Is that okay?
Yeah.
So A is what?
Huh?
A is X is not equal 0.
Yeah.
Right? So
Yeah.
it's like neither X and Y are not actually 0. Okay? So right here we have the De Morgan law. You just operate like this. So this actually is two law. Just tell you A and the B bar equals A bar plus B bar. So this notation is faster than Java notation. That's why I like to operate in this notation. Equals A bar and the B bar. Okay. Okay, negating the logic expression is the same, negating each term and changing its operator. Okay, the pen operator take precedence, so you go first. Okay, whatever. So right here, okay, let's just look at this. A less than 5 and B equals 3. The negation of this is either A greater than 5, greater equal to 5, or Y is not equal to 3. Right? You think about this.
Yeah.
And this one, so actually, here also tell you something. X less than 5 bar equivalent to X greater equals 5. X equals 3 equivalent to spar equivalent to s not equals 3. Is that okay?
Yeah.
This is not too hard, just some sort. Okay, it may help to read these examples out loud in English. Try to understand it. Okay, if I don't want whatever this, I don't want to read. Okay, here. Okay, Boolean variable to store true or false, you need a Boolean variable. So any variable that you store is a Boolean variable. So even flag is equals to n take modulo by 2 equals 0. So if n divided by 2 small remainder is 0, that means n is even, right? And if x greater than 0, that's a positive flag. Is that okay? So here it's actually if this is even, okay? So that's an even flag. So now that this one's a Boolean method. So we have Boolean variable, Boolean expression, Boolean method. Now it's Boolean method. So here is a Boolean method. We pass x is single digit, means it's greater than -10 and less than 10 for any integer. Then you would return true. Otherwise, you will have double digit for any integers, right? So that's integers. So that is a single digit, okay? And so it's single digit like this, and this is single digit, okay? And then it's single digit, that's fine. Validating input. Okay, let's not jump too far here. Let's let me write some program for this Boolean method, okay? So for Boolean method, I want to show you the Boolean method. Let's show you multiple. Okay, let's try multiple. Let's look at the Boolean variable and the Boolean method, okay? First, I have a Boolean, and then let me have an integer, n equals 10, okay? Then I will have this Boolean and 2 equals n take modulo by 2 equals 0. Boolean and 5 equals n take modulo by 5 equals 0. Boolean and 10 equals n take modulo by 10 equals 0. Knowing what I'm trying to do? Knowing what I'm trying to do?
Wait, no.
Okay, I'm done. So, right here, right, I have an n equals 2. Okay, right here, right? Let me clean the page, okay? Okay, clean the page, I go again. Okay, so 10 is a multiple of, so this one is proven. If this number n take modulo by 2 equals 0, I say it's multiple of 2. If not, the n2 will be false, right? Here, same thing, if n is multiple of 5, divided by 5, remainder equals 0, then I say it's n5, right?
Yeah.
And then if divided by 10 equals 0, for the remainder is 0, I say it's a multiple of 10. So for 10, I try this, is pass. So here, let me do something. So here I have import java.util.scanner. Right in here. Okay, here, let me see. Okay. Right here. Let me try this. Okay. Here I say actually right? Enter a number, right? And then I say scan. I teach you this already, right? Scanner for the I/O part, right? And then here I have n equals in dot next integer. Okay, so I can read in any number now. Okay, enter a number. I say 95. So it's only a number. Is only a multiple of 95. Say here I say 110, right? And here I say, right, it's only multiple 2. And if I want to make it work for many times, I can do this. And here set up a Boolean condition. Down equal false. So the first time I want to repeat, right? I really want to repeat. So the first time I say down equal false, I will get in. Not done. Well, not done. Well, I'm not done. Enter some number over here. And here I say 999 to exit. Okay. And then here I do something, doing something. Okay, here. And then here I say if, okay, if I detect a value 999, I'll get out, but actually I will also check whether 999 is a multiple of something. Okay, so here first I ask for something. You give me a number, okay, I give you a number, and then you analyze for me whether it's a multiple of 2, 5, and 10. And then after that down, if the number I enter is 999, I'll get out of my loop. Okay. So right here, let me run it. Okay, here I have need to be this, not assignment. Okay. And I go, right? So first I test the 999. It will get out, right? 999 is not multiple or anything. Now, let me try anything else. So like here, let me try 2, 7, 34, right? 17. Oh, I didn't do some wrong thing in there. So here I enter 97, 87, 25, and then 50, right? So this become a checker for multiple value. So remember what's important here. I'm using a few things. I'm using the Boolean variable as a flag. I'm using Boolean variable as the status check, right? Whether which one it is. And that flag actually useful here to get out of the loop. I'm using Boolean variable for the checking, for the repetition checking. I'm Boolean variable to do my decision. Okay? So that's a good example to give you the idea of reading something in and checking, and also how to use a couple of situations. How can you use your Boolean variable? So, and Boolean function is to pass something to there, and then validating the input is like it's just like what I did actually. It's just to detect some condition. If that input is not our format, we just don't do it, something like that. Okay. So the next one is example program. We have an example program. You have a scanner. Okay, let's show this. You have a scanner, and then you can read some number in. It has double value. Then actually we will put out this. Okay, so you check format. So in that has double means that whether I'm reading the double or not. If not, then I read that as a string. So now let's look at its example. So right here, it actually is validating the input. So in order to validate the input, I actually create a scanner, right? So actually I enter a number. So my number is next double. So I print out that log of x and then print it, okay? And then if x greater than 0, I do this. Okay, anyway. Then there's a type mismatch problem. So I can actually check if it is not double type. You say you type a hello, you will have mismatch problem. So here, before we read it, actually I check if something, then actually if it is not a double, then we actually will print this and then return. So that actually is to check whether the input number is a double type or not. If double type, if not double type, I will actually print out it's not a number, and then will return, and then actually ask you to enter again. So that's a checking of your input string. So that checking of the input string will be useful over here. So the main program is over here. We prompt to ask you to enter a number, and then checking if the number is double or not. So if not, you return, means the program will stop, right? If yes, you allow it to be processed. Okay, so if yes, if not, then you get out. If yes, you read out double number into here, and then say if it's greater than 0, then if yes, we calculate for the log. If not, we say it's undefined. So that's the longest program. Say I enter -1, I should get that it's not a valid number, okay? It's undefined, okay? Now I run again. If I type these kind of things, it's not a number, right? If I run, and then I say log of 10, right? So that's the program it says. So if you want to check the format, it actually has the hashtag double thing, and then you go to there. So actually let's modify our program now. Not done here, okay? Let's go back to our program. So this is well not done, and then what we need to do right here is using the if statement, and then here if input in that has next integer, right? And we do this. We do this, right? So if it has an integer, we go into here, right? And then if not else, we do this thing, right? So I previously actually put 999, right? So here, actually I also use this, okay? So here, if I'm not an integer, I'll go here. When I go here, then I'll say if my actually let me do this. And let me have a string t equals in the next line. I read in a string. If it is not a integer, I read in a string, right? And then if the t equals exit, then what? Then I will also say done equals true. Else do what? Okay? So here, let's do this. We continue to read in every time, right? If it's 999, actually, I'll calculate 999 and get out. That's one thing. If not 999, and then I actually type in equal exit, it will not be accepted for integer, but you will go here, and then you will say if this equals exit, then I set down equals true, and then I go back, and you will get out, right? And then if it's not even exit, it's something you type whatever number or whatever integer, whatever string, it's not actually a number, then I'll get out. Okay, so I'll actually add for a new one. Now actually let me run it one more time. So here, let me try the first one. I just type exit, right? It get out, right? The program stop, it get out. And then right now, let me run again. This time I type some arbitrary thing, right? Now I give it a number and then arbitrary thing, right? So it actually have a wrong info type, and then I give it a number. So there's a little things that I need to tune here, right? So when we write program, we see some little things you need to tune. Is here I need to put a \n because I put in some wrong format. It doesn't change the line. So let me see this one will operate. You know, we need to improve our program, even it's not originally solved. Right now, it's better, right? Something like that. Is that okay?
Yes.
So that's the program for multiple. That's the program for multiple, and this has next integer, has next double, is used for validation of the validation of input format. So first, when we input something, we set up a scanner, and then we prompt. After we prompt, we check for the format, and if the format acceptable, we're going to doing something. If not, we just break or return or just loop back for the while done to take care of it. And this format, the one he gave actually one time deal, he only can enter one times. But the program I give you for this, it actually will loop back to SU for another one, loop back for another one, until you type something that matching the sentinel. Sentinel is someone who guard against a door or something. It will allow you to get in or get out. Okay. So 999 and the symbol exit is used as a sentinels. And for down is a flag. We actually right here we guard against the loop. If it is not down, we go into here. If it is down, we will set true down to be true and then get out. Okay. So here we finish this chapter 5. We actually give you this check-in for the input. We give you Boolean method, a Boolean variable, and also De Morgan rules for the day. Okay? And then, have you done your homework last week?
Oh, I didn't finish.
Yeah, so over the weekend, I try not to. Last time I give you 5152, right? Let me do something. Okay, because you are doing this the quadratic. So let's do this quadratic one. That's helping your math anyway. 5, 6. I'll give you one more, okay? But finish that and send it to me. Okay. This guess my number. I want you to do this guess my number.
Exercise 5?
Yeah, 5, 5. 5, 6. 2 of them, okay? Over the weekend, try to finish that. And last week's homework. Is that okay?
Yeah.
Okay, any question for today?
No.
Yeah, that's it for today.
Okay, thank you.
Okay, bye. Let me know if you have any question, okay?
Okay.
Bye.
Bye.